Good day, students, and welcome to Lecture 8 of the Allen 2016A Electronics 1 course. I'm your lecturer, Mohammed Dango, and today we'll be going through the full wave bridge rectifier. Basically, in today's lecture, we're going to look at the power supply again, and then it's just the full wave bridge rectifier all the way through. You can find this information in your textbook, Chapter 2, pages 68 to 84. And students, please remember anything said or done in this lecture can and will be used as a question in the test or exam. So a recap on the power supply, students. As you know, we've already looked at the transformer and we saw that there are two kinds, this normal one that you see here and the center tapped transformer, which splits the secondary coil into two outputs. We then know that we have a rectifier circuit as the second component of our power supply. We've taken you through the half wave rectifier as well as the full wave center tapped rectifier circuit. The full wave center tapped rectifier circuit has two diodes and the half wave rectifier circuit has one diode. We then have a capacitor filter circuit, which we'll be looking at in the next lecture, and in the next lecture we'll then be looking at the voltage regulator, which gets us a very nice straight line DC output. In today's lecture, student, we're going to be using a normal transformer and we're going to be using the full wave bridge rectifier, which is composed of four diodes. Now, students, a recap on our transformer. The transformer equations, as you know, the primary voltage and the secondary voltage can be determined using the number of turns. We have a relationship between our currents and our voltages, but really the thing that you need most is your turns ratio, which gives a expression for all the variables in our transformer. And finally, remember, whenever you are doing a calculation with a transformer, ensure you are using both peak or RMS for your primary and secondary values. Don't have one side peak and one side RMS, because that's just going to mess up everything. So students, here we have the schematic of our full wave rectifier circuit. As you can see, we have four diodes connected in a bridge configuration. So the P side of diode 1 is connected to the N side of diode 4, which is connected to the top end of the secondary coil. We then see the P side of the N side, of diode 1 is connected to the N side of diode 3, which is connected to the load resistor. We then see diode 4's P side and diode 2's P side are connected to each other and connected to the other end of our resistor. And then finally, the N side of diode 2 and the P side of diode 3, they are connected together and they are connected to the other side of the secondary coil of our transformer. And what we're going to see through this lecture, students, is our transformer's AC line input, which is this nice sinusoid, which also appears at the secondary, but stepped down, is going to be rectified into this very nice pulsating output waveform. So students, now that we're familiar with the schematic of the circuit, let's go and perform an analysis. Now the analysis for the full wave bridge rectifier can basically be broken up into two parts, where we examine the positive half cycle of the input, and we then examine the negative half cycle of the input voltage. And that input voltage that I'm talking about is this one here that appears at the secondary side of the transformer, which is simply a stepped down voltage of the primary side transformer input voltage. So with that said, let's crack on ahead with the positive half cycle. So students, looking at the positive half cycle of our input, we know that you're going to have some peak voltage that the positive half cycle is going to reach. And during the positive half cycle, we're going to assume that diode D1 and D2 are going to be the diodes that turn on, and diode D3 and D4 are going to be the diodes that are switched off. And because D1 and D2 are going to be on, I've left them in the circuit here, and D3 and D4 are off. That's why they are open circuited. Now you'd have noticed, students, that I haven't yet replaced our diodes with their equivalent models, and there's good reason for that. So let's take a look at that in this next slide. Now students, although we know that during the positive half cycle, diode 1 and diode 2 are going to be the diodes that conduct, the positive half cycle can also be broken down into two distinct sections. As you can see from the plot over here, I have this first section which is between 0 and 2 times the diode on voltage, And I say that during this region over here, diode 1 and diode 2 are going to be off. But then students, once my input voltage rises above 2 times my diode on voltage, I say that I'm in this region over here between the input peak and 2 times the diode on voltage, and I say that during this time diode 1 and diode 2 are on. Now there's good reason as to why we have 2 times the diode on voltage, and you've probably guessed it by now, but because we have 2 diodes in the circuit that need to be switched on and need to be forward biased, the input voltage has to rise to a point where it is 2 times the diode on voltage before we see an output across our load resistor. So students, let's examine the circuit or analyze it in this region here where diode 1 and diode 2 are off. So we'll perform a KVL, and from the KVL we get this expression where the input voltage minus the 2 diode voltages minus the output voltage is equal to 0. And of course, we've already said that our input voltage is less than our diode on voltage, so we know our output voltage is 0. We plug that into the equation on the top to get this expression. And students, we also know that the diode voltages are equal because we're using the same diodes. So this expression that is right here at the top, students, after we substitute in the output voltage is equal to 0, and we also substitute in VD1 equals VD2, we end up with this expression over here, which says that our diode voltage is equal to a half multiplied our input voltage for diode 1 and diode 2 off. So this expression here basically tells us what's going on in this first half of our positive half cycle. Now looking a bit further into this, we know that in order to switch on the diodes, our input voltage needs to be greater than or equal to our diode on voltage. Again, for diode 1 and diode 2 to be on, our input voltage needs to be greater than or equal to our diode on voltage. So if we simply rearrange this expression over here, we can see that our input voltage needs to be greater than or equal to 2 times our diode on voltage in order for diode 1 and diode 2 to switch on. And we know that when our input voltage is anywhere less than 2 times our diode on voltage, both our diodes are going to be off. So we've basically analyzed the circuit and proven that in order for the circuit to conduct and to switch on, our input voltage needs to rise above 2 times our diode on voltage. Okay, so then let's actually rise up above 2 times our diode on voltage. And on this slide, students, we're going to be working in this region between our input peak and 2 times our diode on voltage, where D1 and D2 are on. So because our 2 diodes are on, we can replace them with their equivalent models. We're going to use the constant drop model here. So we have our diode on voltage, and each of our diodes are replaced by our source. And of course, D4 and D3, they are not conducting, so they are open circuited. And of course, here we can express our input voltage as being greater than or equal to 2 VD on. So we know that we are operating in or analyzing this region over here. So now that we are in this region, we know a current is going to flow, and let's just trace that current for you students. Let's follow the blue lines. So ID is going to flow from our secondary coil. It's going to hit this point, and it's going to go into our diode 1, through our diode 1, out, across into our resistor, through our resistor. From there, it's going to come back this way, jump over this line, quite a long track, into diode 2. From diode 2, it comes out and then back into our secondary coil. And that's how we see the flow of current for the positive half cycle of our full wave bridge rectifier. And if we were to perform a KVL in this loop, KVL, very simple, we get this same expression from the previous slide, but now we know that our output voltage is not 0. All right, so what is our output voltage at this point? Well, the expression for our output voltage is simply going to be our input voltage minus 2 times our diode on voltage. And it's very simple for us to get that, students. We know that we have an input voltage which comes in. and then it is subtracted by 1 times diode on voltage, 2 times diode on voltage, which leaves us with our output voltage is V in minus 2 times VD on. And that's simply from rearranging this expression to make our output voltage the subject. And now, students, that we have an expression for our output voltage, we can determine the maximum output voltage that we're going to get from the circuit. Our output max, we need to know it's going to occur when our input is at its peak. Our peak is over there. So our output max voltage will happen at our input peak minus 2 times VD on. Now, students, we can work out the load current very simply using Ohm's law. Our load current is the same as our diode current. As you can see, here's your diode current, flows through the first diode, becomes the load current, flows through the load resistor. And we use Ohm's law, which is V out, this voltage here, across the resistor, which is the load resistor. We have an expression for V out, students. Substituted in, there is your equation for the load current. And finally, the maximum load current, or the maximum diode current that we're going to see in the circuit, we then replace our output voltage with the maximum output voltage, which we know occurs when we have our input voltage at the peak. And this is the expression for the maximum load current, or the maximum diode current, that we'll see during the positive half cycle for our full wave bridge rectifier. Now, students, it's always important to ensure that the maximum diode current is less than the peak forward current of our diode to make sure we avoid any damage. And if you were in lecture enrichment session 1, Dr. Schumer took you through this specification of the diode, so you are well aware of it. Next up, students, I'd like us to validate that our diodes are in fact on and our diodes 3 and 4 are in fact off during this operation of the full wave bridge rectifier. So we know that for any diode, if we want the voltage across the diode, we simply say the P side minus the N side. So let's go ahead and do that for all 4 diodes. So starting at diode 1, students, this is the P side. We know that at the P side we have V in. So that's this node over here. You remember nodes from circuits? Yes, you do. So this node over here is simply V in. And so for our expression, VD1 is V in. And then we need to minus whatever we see on our N side. And this node over here, which is our N side, is simply V in minus VD on. So V in minus VD on, that's the voltage that we're going to see at this node over here. And that node happens to be the N side of our diode. So we can see that V in minus VD on, and we simply solve that and we're left with VD on, and that validates that diode 1 is in fact on. Now then, moving on to diode 2. If we look at diode 2's P side, we know that the P side of diode 2, that is this node over here, quite a big long node, we know that the voltage at this node is simply VD on. And if we look at the other side of this diode, which is the N side, this big node over here, where current is then going to return to our secondary coil, because it's the return path for current, we know that this is our reference ground point of 0. And that's why the expression for VD2 is our diode on voltage on the P side minus 0 gives us VD on. We validated that diode 2 is in fact on. Now moving on to diode 3, students, we want to validate that it is in fact off. So for diode 3, if you remember, the P side was on this side over here, and we've already shown that this is our ground reference point of 0 volts. So our P side is at 0 volts. And if we look at the N side of our diode 3, well, we've already calculated or determined what this node voltage is. This node voltage is simply V in minus VD on. And we see it in this expression, V in minus VD on. And we have a minus there because it's on the N side. So we see that the voltage across diode 3 is minus V in plus VD on, which is going to reverse bias our diode, so we know it is in fact valid to say it is off. Finally, students, we're looking at diode 4. Let's do the same thing for diode 4. If you are to remember, for diode 4, our P side is over here, and we've already said that this node voltage is simply VD on, and our N side of our D4 diode is this node over here, and we've already said that this node is simply V in. So here for our diode 4, the voltage is VD on, P side, minus V in, N side. We end up with minus V in plus VD on. Yes, we validated that D4 is in fact off. So now, students, we can move on to the negative half cycle. During the negative half cycle, students, you can see that our input voltage is now applied at this end, and we can see on our primary side we've also swapped around the sides because it's the negative half cycle. And during the negative half cycle, the analysis is going to be carried out exactly the same as we did for the positive half cycle. So we start off with assume D1 and D2 off, D3 and D4 on. So looking at our negative half cycle, once again, students, we have two stages of our negative half cycle. First is where D3 and D4 are off, and the second is where D3 and D4 are on. And now, students, exactly the same way as we did for the positive half cycle, we analyzed the circuit, and we analyzed it in this first section over here, which is between 0 and negative 2 VD on. And we do a KVL in the circuit, and we know that because we are in this region over here, we have no output voltage because we're not going to have a current flowing. We haven't yet forward biased our diodes, and when we go through this KVL, just as we did in the positive half cycle, we end up with this exact same expression, which says that our input voltage needs to be greater than or equal to 2 times our diode on voltage in order for D3 and D4 to be on. And if our input voltage is anywhere less than 2 times VD on, D3 and D4 are going to be off. And then, students, again, exactly as we did in the positive half cycle, we then looked at this second section over here, which is between 2 VD on and the peak of the input voltage. And we said that during this section, D3 and D4 are going to be on. So if we then perform a KVL analysis, exactly the same as the positive half cycle, we then calculated our output voltage expression and the maximum output voltage expression. And as you can see, it's exactly the same as the positive half cycle. Same thing with our load current, exactly the same expressions as we got for the positive half cycle. And of course, students, ensure that the max current that we see is less than this diode forward current to avoid any diode damage. And then, students, again, we can perform a validation to see if our diodes are in fact on or off. This time, exactly the same, students. Let's just go with D3. So if we look at diode D3 and we look at the positive or P side of our diode, we know that that is simply V in. So the P side is V in. And if we look at the N side of diode D3, that is simply V in minus VD on. So the voltage that appears at this node over here is V in minus VD on. So that means the voltage across diode D3 is V in minus VD on, gives us VD on. D3 is in fact valid to be on. And again, students, you perform that same analysis with diodes D4, D1 and D2, and you will in fact validate that D1 and D2 are off and D3 and D4 are on during the negative half cycle, but only when our input voltage is greater than 2 times VD on. So, students, we've analyzed both the positive half cycle and the negative half cycle of our full wave bridge rectifier to get to our output voltages and currents. And here we have the equivalent circuits. If you still don't remember, this is the positive half cycle, this is the negative half cycle, and I've indicated which diodes are off. They are the ones that are in red, and the diodes which are on, they are in color, green and blue. So, students, on this slide, I want us to look at the maximum reverse voltage. And basically that is the non-conducting diode voltage that we are going to be looking at. So looking at our positive half cycle, we know that D4 is one of the diodes that are off. So let's determine the voltage across D4. We know that at this node over here we have V in, and we know that at the P side we have VD on. So we do our simple VP side minus VN side, and we get the expression for our diode being off, which is minus V in plus VD on. Yes, we did this when we were validating which diodes are off, and we saw that all the diodes that are off had this expression. So we know that the maximum reverse voltage is going to occur at our input peak voltage. So therefore, our maximum reverse voltage is our input peak voltage, negative, plus by our diode on voltage. And students, in order to avoid breakdown, we need to make sure that we spec our diodes accordingly, and that is our peak inverse voltage, which is equal to our breakdown voltage, and that must be greater than the magnitude of our maximum reverse voltage, which is simply the magnitude of minus V in peak plus VD on. Next up, students, let's have a look at the waveforms that we see in our full wave bridge rectifier during the positive and negative half cycle. So here we have the positive half cycle equivalent circuit or resulting circuit, and here we have the input voltage waveform, positive half cycle moving into the negative half cycle. So let's stick with the positive half cycle. We know that our circuit is only going to switch on and conduct when we have passed 2 times VD on, which is this point over here. So if I drop a line from that point onto our output voltage over here, we know we're only going to see something at the output at this point. So that's why we see an output starting for our positive half cycle. It then hits a peak output voltage, and we know that our peak output voltage is simply whatever our input peak is minus 2 times our diode on voltage. And that, students, is simply the positive half cycle and the resulting output voltage waveform. Now, if we were to examine what's going on with our diodes, if we look at diode 1 and diode 2, we know that these are the 2 diodes that are going to conduct during the positive half cycle. And they will only conduct when we have a diode voltage that is greater than our diode on voltage. So that's why at our diode on voltage, we see our diode switch on and they start conducting, and they hold that voltage at the diode on voltage. Of course, the voltage across the diode doesn't go greater than the diode on voltage. And if you're looking at a silicone diode, we know that this straight line will be at 0.7 volts. And then, students, once our positive half cycle hits this point over here, which is on the falling edge, where it falls below 2 times the diode on voltage, we know that both our diodes are going to switch off, and that's why we see our diode on voltage is no longer held and it starts to decrease. Looking at our diodes 3 and 4, which are going to be off during the positive half cycle. So because of the way the circuit is built and configured, we know that the voltage across our diodes D3 and D4 is pretty much going to be our maximum reverse voltage. And the maximum reverse voltage happens at this peak point, which is minus V in peak plus VD on. So during the positive half cycle, we can see that VD3 and 4 are in fact reverse biased and they are switched off, and VD1 and D2 are in fact forward biased and they are switched on. And the resulting output voltage that we see across our load is simply this pulsating DC voltage, which has a peak value of V in peak minus 2 VD on. Now, students, looking at the negative half cycle of the full wave bridge rectifier, it is exactly the same approach that we took for the positive half cycle. The only difference here is that D1 and D2 are off and D3 and D4 are in fact on. But when we look at our diode output voltage, we see that although we have a negative half cycle at our input, that is flipped around and we have a positive half cycle at our output. And that's why we have a full wave rectifier and not a half wave rectifier. And also to note, students, that the frequency of the output for our full wave rectifier is 2 times that of the input voltage. So at the input voltage, we can see that the time it takes to complete one cycle, and it ends there. So that is the frequency or the period of our input. However, if we look at our output voltage, it starts off here, it goes along, goes along, goes along, it ends here, and then it begins to repeat itself. And we know that as soon as it repeats itself, we are now into the next cycle. So here we can see we have one cycle and a second cycle, which means that this frequency is 2 times that of the input voltage. And now, students, that we're familiar with the waveforms, we can go ahead and calculate the average or DC output of our full wave bridge rectifier. Again, I've got the two schematics of the forward or positive half cycle and the negative half cycle equivalent circuits. And if we look at the output voltage curve, the average or DC is simply this area under the curve. And in order to determine that, students, we take this expression over here, which is 1 over our period, the integral from 0 to our period of our output voltage. So basically, students, we're integrating from 0 all the way to our period, which is 2 pi. So we then plug that into this expression over here. We get 1 over 2 pi integral from 0 to 2 pi. Of course, our expression for our peak voltage, which is V in peak minus 2 times Vd on. Remember, that's our peak voltage here, multiplied by sine omega t, because yes, this is a sine wave. And once we then resolve this or solve it, students, our output voltage DC value for a full wave bridge rectifier is given by expression 2.9. And then simply to determine our output current, we take our output DC voltage and divide it by our load resistor. That's simple Ohm's law, you know it, and that is expression 2.10. All right, students, now that we've covered the bridge full wave rectifier, let's go through an exercise quickly. A bridge full wave rectifier is connected to a 150 ohm load resistor. The peak output voltage is 18.6 volts, and the rectifier diodes are silicone diodes. The AC input voltage to the primary side of the transformer is 230 volts RMS at 50 Hertz. Assume constant drop diode model. So first thing is draw the circuit diagram and then determine the secondary peak voltage, maximum current through the conducting diode, the average or DC output voltage, and finally the maximum reverse voltage across a non-conducting diode. Right, so that's a very simple one for us to do. Draw the circuit diagram. Well, students, you should be familiar. This is the full wave bridge rectifier circuit diagram. It has a transformer, which is normal, not center tapped. It has 4 diodes in a bridge configuration. Always make sure you draw your diodes in the right direction. Nice way for me to remember it is I know 1 and 2 are going down, 3 and 4 are going up. That's the best way to remember it for me. And then we have our load resistor over here. Always remember to fully label your circuit so you know what the hell is going on. So we know 230 volts RMS is over there. We know that we have an output peak of 18.6, load resistor of 150 ohms, and I should have labeled these diodes as silicone. So here for our first thing, the secondary peak voltage, Vs peak, we simply take our output peak voltage and we add 2 times our diode on voltage, because we have our output peak voltage. And if we simply work back, we know that in order to get our diode peak voltage, it was our input voltage, which is expressed as our secondary voltage in this case, and it was minus 2 of these diode voltages. So we just add it back to our output voltage and we get a very nice 20 volts as our secondary voltage, or you can call it your input peak voltage. They then want us to calculate the maximum current through the conducting diode. So because we have our output peak voltage, we know that the maximum current that the circuit will draw because of this load resistor is determined using Ohm's law. so 124 milliamps. Next up, the average or DC output voltage. Well, students, you simply take the expression that we derived in the previous slide and you plug and play. So 2 times our output peak voltage divided by pi gives us 11.8 volts. And then finally, students, the maximum reverse voltage across a non-conducting diode. Well, that again we know is going to happen when we hit our peak input voltage, or in this case minus V in peak plus VD on. And we saw that we've used this expression to validate that diodes were in fact off in our full wave bridge rectifier. So if we solve this expression given the numbers that we have, we see that our MRV is minus 19.3 volts. And bonus, we know that our peak inverse voltage, which is our voltage breakdown, needs to be greater than our maximum reverse voltage, or the magnitude of our maximum reverse voltage, so that we do not damage our diodes. Alright students, so that is the end of rectifier circuits, and I'd like to tie it all together using the next two slides. So on this slide over here, students, I've got all three rectifier circuit schematics, and with each schematic I've given you the output voltage equations for the normal output voltage and the maximum output voltage, as well as the diode current and the maximum diode current. I've then given you the DC or average output voltage expression, followed by the DC current output expression and the maximum reverse voltage expression. So this will be given to you in your test and exam in a data sheet, but I'm giving them to you here so you can familiarize yourself with it. And of course, this is a very nice summary of the schematics of each circuit, how to label each circuit, and of course the various equations and expressions that we derived in the last three lectures for these different rectifier circuits. And then finally, students, here we have the waveforms that are associated, well, rather just the input and the output waveforms associated with our three rectifier circuits. We know that for our half wave rectifier circuit, we're only going to conduct on our positive half cycle. On the negative half cycle, we're not going to see anything. That's why our frequency of our input is equal to the frequency of our output. And of course, the peak of our output voltage is our input peak minus our diode on voltage, because we only have this diode to drop a voltage. Next up, the center tapped full wave rectifier circuit, students. We know that it center taps our transformer, so we're going to have two voltages, VS1 and VS2, and that's going to give us two loops, this top loop and this bottom loop. And of course, for VS1, we're going to have a peak voltage which is half of our primary side voltage, right? Don't forget that, students. VS1 and VS2 are simply equal to half of your peak, or your primary side voltage. So of course VS1 follows this direction and VS2 is basically VS1, although it is inverted. And we then see that the output across our load resistor for our center tapped full wave rectifier circuit, we have a peak output which is the input peak divided by 2 minus our diode on voltage. And because we have this divide by 2, we know that we're not going to get much voltage across our output, so not much power that's going to be going through this full wave center tapped transformers, full wave center tapped rectifier circuit. Although the frequency of the output is equal to 2 times the frequency of the input, as we see this circuit repeats twice during one cycle of the input. And then finally, students, we've just been through the full wave bridge rectifier. Personally, this is my favorite one, and we saw that we have the positive half cycle followed by the negative half cycle, and of course we have our output which has 2 times the frequency of the input, and a peak voltage which is the input peak minus 2 times the diode on voltage. Now when we compare this output to the full wave center tapped output, this is the input peak divided by 2, and this is simply just the input peak. So that's why we see a lot more power coming out of the full wave bridge rectifier circuit, And that's why the full wave bridge rectifier circuit might be preferred. But then why would you want to have use of the full wave center tap transformer circuit? Well, students, the first thing I can see is that there's less diodes, which means less components, which means you need less space, you need less money, less resources. Perhaps that could be one reason to use that circuit. Or maybe you have a center tap transformer that you'd like to try out. Well, you can also simply take a center tap transformer and you can ground the center tap, and you can then use it as a normal transformer to build a full wave bridge rectifier diode circuit. And I'm saying that, students, because I know for the project you are going to be supplied with a center tapped transformer, and it's then going to be up to you to decide which one of these rectifier circuits you want to use. And I've literally given you the answer as to how you can convert a center tap transformer into a normal transformer and then use a full wave bridge rectifier so that you can get maximum power out. But of course, whether or not you want this maximum power, well, that's all up to you and your design. And that brings us to the end of rectifiers, students. We went through the power supply in this lecture, we went through the transformer, but we didn't do the half wave rectifier, we did the full wave bridge rectifier. Apologies for this error. And of course, I summarized all the rectifier circuits at the end of this lecture. And in the next lecture, we'll be covering the capacitor filter. So students, if you're still unfamiliar with any of the stuff we covered in this lecture, please check out chapters 2, page 68, and I think it's supposed to be till page 81, not 71. And if you find any other errors in this lecture, please bring them to my attention, and I'd always appreciate any constructive feedback. Have a good day. Goodbye.